Going to discuss the operation of ideal transformer. This particular be treated as the formal beginning of discussion on the performance measures and operational aspects of practical transformer. This discussion or these measures also requires the concept of magnetic circuits and the AC circuit fundamentals that we have already covered. As a recap, the operating principle of the transformer is revisited here. So, the single phase transformer is best represented by the two coils coupled, or you can say bound on a magnetic core. So, this particular is representing a magnetic core. This particular is one of the winding that is designated as primary, other winding is the secondary. So, when say the primary is supplied by the AC source, it is giving rise to the current I1, that particular will also be AC. It is giving rise to the flux, that particular will also be sinusoidal. This flux is linking to the secondary and that is resulting into the induced EMF in the secondary. When say we are connecting the load, there will be a current. So this particular process we have already covered previously. Now it is needless to mention that the two windings are electrically separated but coupled magnetically. So the transfer of energy from primary to the secondary or from one winding to the other winding takes place through the electromagnetic induction, which is regarded as the transformer action. The ideal transformer is basically based on some assumptions. So these assumptions are the winding resistances are taken as 0. There is no leakage flux, so whole of the flux or all the flux which is established by the primary is linking to the secondary. So you can say the leakage reactance is taken as 0. Previously in the magnetic circuit we have gone through that the magnetic core is resulting into the two type of losses, hysteresis and the eddy current losses. However, these losses are neglected in the ideal transformer consideration. Now just mention that the two coils are electrically separated but they are coupled by the magnetic media. So for this coupling we need a magnetizing flux, and that magnetic flux can be established by the magnetizing current. So here the assumption is that very negligibly small magnetizing current is needed to establish that flux. Now this particular has already been discussed. Only thing is now we are giving to the mathematical aspects. So the AC supply which is given to the primary, it is having a frequency f. So this particular is of sinusoidal nature. Because of this the current will be sinusoidal. There will be a flux also which will be sinusoidal. Here say the operational aspects which are discussed, that is on the no load, then I will be covering the loading aspects as well. So the flux is sinusoidal, that particular is made by phi m sin of omega t, where say phi m is the maximum value of the flux. Because of this sinusoidal flux there will be induced EMF E1 and E2. So those particular E1 and E2 are decided by the Faraday's law. So that is giving rise to the n d phi by dt. However, the Lenz law suggests the direction. So that particular direction is giving, with the direction sense, it is giving minus n d phi by dt. So this negative sign is basically suggesting that it is opposing the cause, which is the current. So this particular is directed opposite to the V1. Now say the flux expression is substituted in this, and when say the derivative is carried out, we will be able to find out the instantaneous value of the induced EMF E1 and E2 likewise. Then we have to have a phasor analysis. So we will be writing these two terms suitable for the phasor analysis. So only difference which has been carried out here, that the cosine term is represented into the sine, because the sinusoidal was our reference phasor for the flux. Another important aspect, that we will be writing this into the standard form of omega t plus minus theta degree. So it is to be written accordingly. Now these particular are summary, and we have gone through that the RMS value of the voltage can be calculated with the help of the peak value or maximum value, likewise such that Vrms is equal to Vm upon root 2. So for this purpose we will be writing corresponding to this E1t, there will be E1 max, and that E1 max is nothing but what has been obtained here, N1 phi m omega. So here say the omega is substituted, that is the 2 pi f, so the expression comes out to be like this. When say we are looking for the RMS value, it will be E1 and E2 likewise. Now the RMS subscript has been eliminated for the convenience of the writing, so it is the uppercase nomenclature E with the subscript 1 and 2 to represent the primary or the secondary winding. Now we have to have the analysis. So this particular is a summary what has been discussed. The flux expression and the instantaneous expression of one of the voltage is written here for a reference. Now if suppose we are finding out that the N1 by N2 is a turns ratio. So N1 is the number of turns of the primary winding, N2 is the number of turns of the secondary winding, then the turns ratio is defined as A is equal to N1 and upon N2. So when say you are substituting these RMS values, so you will be getting E1 upon E2 is equal to V1 upon V2, which is equal to the turns ratio. This V1 V2 are coming out because previously if you are looking at the expression is exactly same on the instantaneous basis. So with this background we can now frame the phasor diagram. So this particular flux is taken as a reference, so we will be marking, let's say it is coinciding with the horizontal axis. Now this induced EMF E1 is lagging by 90 degree to the flux. Similarly the E2 will also be lagging by the 90 degree to the flux. Only difference in the E1 and E2 will be the turns ratio, or you can say the scale arrangement. So that particular lagging arrangement is drawn likewise E1 and E2. Now the V1 which is coming out to be of equal magnitude to that of E1, but that particular is drawn on the opposite direction, like say in this direction, to give a clear cut understanding when say we will be developing the complete phasor. So the secondary side is represented on say this particular downward direction, where say the primary side is represented on the upper direction, so we can separately visualize what is happening there. So V1 is marked likewise, and that particular is exactly of minus E1 value. So we will be coming to that there is a contradiction here. We are writing the E1 is equal to V1, but on this particular we will be writing V1 is equal to minus of E1. So what is the rationale behind this particular contradiction, etc., that will be also explained. So there are say the two arrangement which need to be clarified. So when say the magnetizing current is negligible, how the flux is established? So we are considering that this particular permeability, relative permeability, is approaching to the infinity. You please be mindful, it is of very high value, approaching to the infinity, it is not exactly infinite value. So because of this there will be a negligible small magnetizing current. When say that current is so small that we can easily neglect it. However, the direction of the flux will be the direction of this magnetizing current, and that particular is taken as or coinciding with our representation with the horizontal axis. So this particular is a valid assumption when say we are considering the ideal nature. Now another aspect that we need to clarify, that while say we are writing at one point V1 is equal to E1, and on another time we are putting this negative sign which is appearing likewise. So how what is the significance and what it corresponds. So certainly the magnitudes are equal, but this particular negative sign signifies the direction of the power flow when say induced EMF is acting alone. So when say the induced EMF is acting alone, it will be supplying power to, you can say, connected something on the left side, where say when the input is given, that is V1 is acting alone, the power is transferred to something or say the electrical load on the right hand side likewise. So this particular is a valid assumption. Now we have to consider the transformer under the loading. So the loading means you have connected a load or the impedance on the secondary side. So because of this there will be a current in the secondary as mentioned in the operation of transformer. So this particular secondary current is giving rise to its own flux likewise, and that particular is going to reduce this particular original flux level. However, the flux level has to be maintained, that is a property of the magnetic material, so it will continue to draw the current. So whatever say the decrease in the flux arising because of the N2I2 MMF, that will be counterbalanced by the increase in the current or say the increase in the MMF, which is N1I1. So whatever say has been represented on the secondary, its counter current or reflected current on the primary will be I2 dash. In the ideal case, when say the other currents are neglected, so I1 will be I2 dash. So that counterbalancing of the MMF is established, and that particular is giving rise to that I2 dash upon I2 is equal to 1 upon A. As mentioned that this I2 dash is equal to I1, so the I1 upon I2 which is equal to 1 upon A, and that particular is translated in terms of N2 upon N1. So here while say the other than the current, the phasor diagram is the same as discussed previously. Here say the lagging power factor load is considered likewise. So because of this, the ideal nature, the angle is coming out to be the same, and so on. Now we have to develop the equivalent circuit likewise. So the primary side parameters are represented like V1, I1. Secondary side parameters are represented with E2, I2, and there is a load impedance. So previously we have gone through that E1 and E2 are related by the turns ratio. E1 is equal to A E2, or you can say E1 upon E2 is equal to A. Similarly, we have discussed that I2 upon I1 is also equal to A. So in that way, if suppose say this particular impedance is translated here, refer to the primary, we have to multiply it by the A square term. So ZL is the secondary parameter, I2 is a secondary parameter. When say we are referring it to the primary side, the current is to be divided by the turns ratio. Similarly, the impedance has to be multiplied by the turns ratio square. So the rationale behind multiplication is to be understood likewise. So ZL dash, which is the impedance referred on the primary side, is evaluated by E1 upon I2 dash. That particular is giving rise to the A times E2 upon I2 upon A, and this particular factor is coming. Similarly, when say we are establishing interested in the equivalent circuit referred to the secondary, so this input voltage has to be referred to the secondary likewise in this way. So in this referral process, or you can say we can eliminate this particular the transformer, and ultimately the resulting arrangement will be like that has been discussed for the AC system. Now as an example, so let the ideal transformer has the turns ratio of 2/1. The parameters are given. We have to draw the equivalent referred to the primary side. also needed to calculate the primary and secondary currents and the input power factor and the load power factor. What is done here? This is the original circuit which is given to us. So the turns ratio 2/1, impedance, load impedance is marked on the secondary likewise. Now you have basically labeled the secondary voltage to that of the primary voltage level. Correspondingly, the current is also labeled at the level of the primary. So as mentioned that we have to multiply the impedance by the turns ratio square. So that particular is 2 square, or we have multiplied it by the 4. So in this particular process, this E1 and 2 E2 they are at the same level. So this particular we can eliminate. I1 is equal to I2 by 2. So we can represent it by one arrangement. On this we have represented the equivalent impedance which is marked over here. These two impedances are added and that particular is giving rise to this particular simplified arrangement. Now the performance measures are carried out based on the same arrangement. So the I1, which is the supply voltage 200 upon 12 plus J6, this particular is coming out to be the rectangular form. This is the polar form of the representation. So this is giving rise to the 14.9 ampere with an angle 26.60. This particular angle is negative, so you can say this particular impedance is coming out to be of inductive nature. Because the supply voltage is given, so E1, which is the phasor of the input, we calculate. So 200 minus I1, because the series impedance was coming out to be 4 minus J2 in the previous diagram. So it is giving rise to the 168.6 with an angle 18.4 degree. The E2, which is related with the turns ratio, that is calculated likewise, so it is giving rise to the value. I2, that is also related with the turns ratio, so that we can easily calculate. It is having the same angle, but the magnitude is getting multiplied by the turns ratio factor. The load power factor, because of the impedance on the load is 2 plus J2, so that particular is giving rise to a 0.7071. This impedance is of R plus Jx nature, so it is of lagging power factor now. Input impedance, that particular is 12 plus J6, so correspondingly we will be having the power factor as 0.8944 lag. So here the input power factor is coming out to be better compared to this, because there was a series element which is of 4 minus J2. Because of this cancellation of the reactive component, the power factor has improved. In this particular discussion, the assumptions for ideal transformer operations are highlighted. The primary and secondary side voltages, currents and the impedances have been referred or related to the turns ratio. So these are the expressions that we have already discussed. The equivalent circuits referred to the primary and secondary have been obtained. So this particular, you can say, the simple process has been illustrated. In the next, we will be analyzing the practical transformer operation and the equivalents. For further reading, you can refer this book.